welcome to Handmade Hero Show. We code a complete game live on stream. We are going to do some nitty-gritty programming right now. I wanted to clean up some of the stuff in our asset system. I've been wanting to do it for a while. You've seen me put some to-dos in there, and earlier today I just decided it's time. And the thing that really pushed me over the edge was I wanted to be able to do stuff like flush textures and so on. And it was just like, look, I'm not going to go add new features to this thing when most of what's in there now is not really that necessary, right? It used to do a little bit more heavy lifting than it did. Doesn't really need to do that anymore. So I'm just going to go ahead and take this opportunity to really like streamline it and just get it into a simpler, more direct state. Now that we know what it needs to do, it shouldn't be that hard. So if I take a look at where, I don't really know exactly what we're doing in terms of texture ops right now. I think they're pretty basic in terms of who does what with them and when. So I don't know. Let me just do a quick, yeah. So I think this is really all that happens right now is we get the OpenGL managed textures thing happening there. And so really, I think most of the texture op actual work is done in here, right? So there's a call to init texture queue, and what that does is it says, here's some memory that we're going to use for these texture ops, and then it actually creates the texture ops inside the memory that you gave it. And I think that's probably fine. In other words, this part probably doesn't actually have to change. But what is going to have to change is when we go, when you actually look in what we wanted to do in terms of texture ops, we wanted to change this add op bit here. And you can see we have a ticket mutex that says, look, when you're accessing the render texture queue, it locks up so that nobody else is going to do anything to the queue while you're in there. Specifically, like inside the OpenGL managed textures, we've got this DQ pending thing. The DQ pending thing, well, I don't know where it actually is. Don't ask me why we didn't just forward declare it, but we actually have the whole thing up on here. I don't know why, but we do. So there it is. Is there can we move that out of here? Does that need to be here for some particular reason? It doesn't really seem like it should have to be there, right? It seems like it should be able to go down here. Was there really a reason we couldn't put it down here? Right? I mean, this needs to know about it, but does it actually need to, does it actually need to be done that way? Can't we just do this? Yeah. Yeah, it seems fine. Where did that go there? Where did that go? Oh, so I guess, well, I don't know. So why was that why was this not picked up? I mean, that's it, right? Oh, I guess because it has to be done this way. Is it actually external? I see. So that's why we put it there. All right, we did have a good reason. We had a good reason. I'm okay with that. We wanted it to be compiled into both cases. So, all right, fine. I'll take that. But anyway, so you can see here we've got really just these two cases where we're doing the DQ pending and the NQ free, need to take the ticket. Excuse me. And then add op when it actually puts something on. So those are the three things that actually do something with the list. What we want to do here is we want to change this around a little bit such that we have some other steps involved in the process as well. And you can kind of imagine how this needs to work. It's a little bit complicated because we want this to be in this part of the code because we want to potentially allocate space for our texture ops that will be, for lack of a better term, flexible in terms of where they are placed in memory. So for example, if we want to, in the future, if we were using a more direct memory model for our, like even our OpenGL transfers, or if you were implementing a Vulkan Direct3D 11 or 12 or a Metal platform layer, and you wanted to basically say, here's the aperture, put the texture in there and go. what we want to be able to do is call to the renderer and say, renderer, tell us where to put this stuff. Right now, we're passing the data into the renderer. We don't necessarily want to do that. We might want to like create a buffer that's known mapped into the GPU address space, copied in there, and then let the transfer go. You know, it's hard to say. Really depends on what platform, whether that stuff matters. You know, sometimes that stuff is pointless, doesn't really matter. And so in this case, we're really more talking about putting it on the right side of the API boundary so that when it does matter, we can do it. But I'm not suggesting it's actually going to matter for us at the moment. It's probably not an issue for us at the moment. So when we call complete texture op and we pass it an op, that's actually going to be the new place where this stuff happens, right? Meaning when we have an op and we need to put it on the queue, it's still going to do basically this. So I don't think we really need to adjust this code too terribly much. This probably looks the same here. And so the nice part is the soft failure case we're running out of ops, we're getting rid of that nastiness now because instead of actually having this copy the op, from now on, when we do complete texture op, this is an actual op we can queue. So this actually goes away, and that dequeue process, in fact, I can put it kind of up in a separate space here, right? This process will now work much more nicely, if that makes sense. So when this texture op comes in here, it just gets linked in, and that's linked in, of course, the networking service by Microsoft, where you can go find other people who work on Web 2.0 or whatever, or 1.3 or whatever web version we're on now, Web Squared. But so when we complete a texture op, we can link it in the exact same way as we were linking it in before, but we now we want to split out that part where we get the actual ops. And the reason we want to do that is because now we want that to be able to fail. Because remember, now we actually handle failure cases. If we run out of, like, we're trying to just do too many textures at once, and we run out of texture ops to do the transfers, that's actually fine. Because now what'll happen, and actually this can go away, right? This whole routine is going to go away. In fact, I'll just delete it, because all of this stuff, this is all actually, all of this code is not necessary. Like, all of this is not necessary. It's all done. Goodbye. So anyway, yeah, the point is when we actually come in here and actually want to do a load. So for example, if we do load bitmap, when we ask for the texture op, what we're going to do is say, okay, if we can get the texture op, then we'll use it. And if we can't, then we just won't. And we'll just force the person to try and load it again, right? And so when it comes through here, it'll say, well, we queued it up for a load, and then we go in and we're like, oh, actually, we can't load it, so we just won't, right? We'll reset it. So in here, what we want to do is say, basically, like anytime you can't finish up what you were doing, like in this case, we can't do it. Now the task got checked up here, so I don't really know any reason why we still have to check it that way, right? So this stuff can actually be placed a little bit more succinctly. This cancel texture op can actually go in here, like so. So that's all good, and I think that's the entirety of the failure handling there, right? That's all we really needed to have happen. So it's just fine. All of this is fine, and that all feels reasonable to me, right? When we look at what's happening here, I don't actually know why we do the task work equals work thing here. I don't get it. Like, I don't see why we wouldn't just assign it that way to begin with. Like, I think it was probably because, oh, I know why. Because we had previously wanted to be able to call an immediate. So since we don't want to call an immediate anymore, we can actually just do this as well. So again, you can see there's just a lot of simplification that can happen in this code now, that we know we don't need a lot of the things that we originally had to have when we were making it work originally, because we just didn't have as much other stuff in terms of support. So now if we look at what actually happens, it's pretty easy for us to condense a lot of this stuff down. You know what I mean? So if we look at what has to happen here, again, we need this function now, and this is going to be where the real fun begins, right? This is where we have to actually start thinking about stuff. And so these texture ops, we're probably going to have a lot less of them. And the reason we're going to have less of them is because we probably don't want to have quite so much memory sitting around being wasted on just transfer stuff. But, you know, in general, we're still doing what we're doing. So in here where we say begin texture op, and we've got the asset queue like so, and we have a width and height. Then what I think we can do here is just every time we want to work with one of these, I think we can use the free list here and just, you know, do the exact same situation. We know we have an actual, we don't have to do an assert, right? We can look at that first free and we can actually see if we got one. You know what I mean? Like this. And looking here, I think when we queue this in, every time when we bring one back, we want to make the next point equal to 0. So I'm going to, in here, also assert that the ops next pointer is 0. Just looking at what's going to happen here, right? So we're going to come in here, we're going to say, look, we need to do a transfer to the card of a texture that's here this much, you know, this big, right? A width by height, there it is. So what I need you to do is I need you to give me back an op that's got that much memory. So what's going to happen here when we actually pull out whatever the first free thing is on the queue, we need that thing to have enough memory. And there's two cases. Either there's one case where the result exists, but it's not enough memory. Another case is when there's no result at all. And what we could say is if there's no result at all, that'll just be a straight up failure case. If there's a result, but the result doesn't have enough memory, then what we want to do is basically reallocate that to be bigger, I think. There's two schools of thought here. Let me kind of tell you what they are. So if we look at how our transfers are going to work, we're going to have two different size textures. And I guess I don't know where we... Yeah, so you can see here. So we've got two different kinds of textures. I don't know if we really want 512 by 512 as our size for things. Do we really want that? Hey, look, this is what we did last time. It's 1 megabyte per, and so we'd only get like 256 of those. I guess I don't know how many things would probably be on the screen at one time in terms of sprites, but like, I do wonder if 512 by 512 may be a little aggressive, right? But I don't know. I mean, if you figure a modern graphics card is like a gigabyte of memory, then I suppose on the high end, maybe you do want to do that, right? I mean, you can always do less. So you could always have a mode where we scale it down. So I guess we do want to start with 512 by 512 and then just say, look, we're going to have 1,000 of them. So you better have a gigabyte in your graphics card. And if you don't, well, you're going to have to wait till we do the lower res switch. And then we'll run on smaller. So anyway, looking at this, what I wanted to try and say there was just that, look, if we look at how much memory we need in terms of transfer space, then really what we've got is we've got 512 by 512 by 4 transfers, and we've got 2048 by 2048 by 4 transfers. This one's 16 megabytes, and this one's 1 megabyte. We don't really want all of our transfer buffers to be 16 megabytes, because if they were, we would end up in a situation where, if they all were that big, then we'd end up in a situation where we're wasting just a ton of memory. Thinking about it here, I suppose a circular buffer would be fine in this case because the transfers generally kind of go out in order, and we don't really need them to worry about completing out of order too much. I mean, there will be some out of orderness to it because they won't fill in necessarily in a proper way there, but you know, we could. I don't think I really want to. Yeah, I don't know. That's a tough one because we could just use a circular buffer for it too and just say, look, there's 64 megs of transfer space available. You just fill it up as you go around, and you can't use more until you retire up through the, you know, it retires in order, even if the thing's complete out of order. So you might have to wait a little longer to get the memory back than you would have otherwise, but that's probably fine. You know, we could do something like that. Just thinking about what that would actually mean. Yeah, I'm gonna go ahead and say that's what we're doing. That just seems better. That just seems way better. And so when we look at how these texture ops work, I think then we rewrite this part too to be even simpler than it was before, as well. So when we do these texture ops, we don't really need to do these as complicated as they were either. When we're running through those ops can really just be instead of a list, they can just be in order. So it can just be a circular buffer, right? So the texture op list is really just something that says, look, I have the transfer memory, right? And I have the transfer memory size. And then I have the transfer memory at. And this in general is just going to roll around. And we'll put in whatever we need there to keep track of it, but we don't need this anymore. And, you know, each one of these texture ops then, it does have a data pointer, but it also would know, in addition to its data pointer, it would know where in the transfer buffer it actually was. So you would know what you could free up to when it was done. You know what I mean? And again, the ops would just go in order. So then you would just have a texture op thing here where it's like, look, there can only be this many outstanding at a time or something like that. That's probably way more than we actually need, but you know, who knows? So then when we have our texture ops, they don't have next pointers, and you're really just rolling around in here and looking at how many there are outstanding, right? So this is the op count, and this is the base op. This is the first op index, and that's it. I think that's really it. So as you push them on here, you just fill those out, and then when it goes to actually retire them, it just retires them in order. And I think that's all there is to it. This, we could say, we could have this happen on 2 threads. I don't think we need to, but if we wanted to, this would be much easier to have happen on 2 threads as well. And so that's kind of a nicer thing to be able to do there also, right? So in here, we just say, look, here's the texture op, and so on. And then all we need to remember in here is we need to remember, like, the two parameters that told us, like, how big this thing was, right? Really, we only need one parameter here, which is what we will retire to. So in some sense, since we have the data, we wouldn't necessarily need that. But what I'm going to do here is say, yeah, I think I may just say, all right, you know, really what we want to have happen here is just something that says I guess, like, free up to memory at or something. So basically, like, that's where, as we're talking about where the, like, high watermark is of this stuff that we have to sort of advance around, that is, you know, that is the value we would advance up to. We could do this in a way that would be a little easier on ourselves, and maybe I would like to do it that way, right? We could just make these be U64s, and then we just mod them into the transfer memory size. So, you know, we would do something like this. So we'd say, you know, what's the bottom free part, and what's the top unused part. You know what I mean? So we could do something like that. I'm trying to think if that's easier or harder. It might be easier. Because that's going to be the entirety of the complexity there is just, you know, it's just going to be like, do we have enough free space given the wrapping point? So, yeah. I'm not sure. Does anyone have any opinions on this? I guess I'll do the U64s for now. I'm going to call it first used, and then I'm going to, you know, call it a used count. So we're just going to talk about the range, and that's, you know, we'll just work with it from there. So you know, that's what we'll do. And then here for texture op, we're just going to say, well, you know, when this thing is done, then the last used is this, right? And that'll be used to essentially free up to that point. So that's all we're talking about here. And the renderer texture queue now, and in fact, I don't need the op list to be what it was here. I'll just make it be that, right? And that way there's no free list, there's no nothing. That's the entirety of the whole thing, and it does all of the operations that way, right? So then it's much easier when we do complete texture op versus cancel texture op. The only real thing we need to do here is like mark when these are completed and when they're not, right? We just need to know if they're completed. So we just need a thing that's here, like that's it. You know what I mean? And so if we have these various texture ops, like, okay, there's complete texture op, and there's like, you know, cancel texture op, I think was the other one. So cancel texture op is just saying that it's completed without ever actually having it, you know, get issued. When we do begin texture op, and you know, I think we probably need to, since we know that again, this is stuff that always happens synchronously. Basically, all this stuff happens synchronously. We don't really have to do anything more complicated. Like, we don't need a thing here that says, like, is it in flight or in progress? Because that's all going to happen completely synchronously. And unless we later decide to make it asynchronous for some reason, then we would add the tracking then. But up until then, we really just don't need to at all. So I think complete texture op actually doesn't do anything. Meaning it's a call, and we probably want the call to be there, but we don't actually need the call to do anything at all. So when we do begin texture op, I'm trying to even figure out why we even care about this at all. So maybe we do need one thing completed that just says, hey, it's ready. Because we make this, and then we're going to, you know, fill it out, but it's not ready to use yet. And so we need to wait until this gets called to know that it's ready, I guess. So I guess we do need one piece of state information here, which is like, is it ready? So we really need like this. something like that. So we would sort of say, yeah, like, you know what, there's a state value. The state value is something that generally can get done asynchronously. So like this is a volatile value in a sense. You don't really have to read it volatile, but if someone were to spin on it, you would want it to be. When we cancel a texture op, we would set the state here to be empty. When we complete a texture op, that says that it's ready to be transferred. And when we begin one, it's pending load. Now, when we begin the ticket mutex on here, like, again, I'm trying to think now. I don't think we ever actually need the mutex anymore. Like, I think we're wait-free now, in a sense. Because all we do is just, hey, we transfer stuff when it's ready, and until it's ready, we don't. And threads don't care. So I think that may eliminate a ticket entirely, possibly. And don't quote me on that because multi-threaded programming is very hard. So, you know, I don't want to say that that's necessarily true yet. But anyway, so in here we would essentially say, look, okay, the state is that we're pending a load, so we don't want to do anything. If you cancel it, we just set it to empty and move on. If you are ready to transfer, then we are ready to transfer, right? And everything's fine. So in order to get one of these, again, it's still going to be the same as it was before, meaning we do have a soft failure case. That failure case is when the op count has exceeded the number that we could support, right? So if we come in here and we see that the op count cannot support it, right? We would say if the queue op count is less than the ops, then we can queue. Otherwise, we cannot queue. You know what I mean? So we look and say, look, can we queue? If we can queue, let's go further forward here. When we do this, we want to say it's going to be whichever one is the queue op count plus plus. Now, this is not actually quite right because, again, we got this first op index, and that's a wrapping value. So actually what we would do here is say, well, if we're going to use one of these, then we need to move it forward one. And so that, you know, definitely does that. But in terms of where we are, we need to take this value, like op index. We need to start at the first op index and then add however much we had there. That then needs to get wrapped around. So we then need to say op index, you know, mod array count q ops to get the, you know, to get us into the circular buffer in the right place. Once we have that, we're ready to go, and we can proceed as necessary, right? So we can say, here's the texture handle. Well, I guess they're going to fill out the texture handle. We don't care about that. So we would say, here's the data to fill in, the transfer memory last used, and the state. And all this stuff goes away, right? So that's, you know, again, pretty nice and clean. But now we have an additional check we have to make. So really, it's not just this. We also have to make sure that the memory that you're asking for is memory that we actually have, right? Because we might not have it, right? We might not have the memory. Now, there's two ways we can, because this is a wrapping buffer, there's two ways we can do this. One way is to actually use split loads. And so what would happen there is if you asked for, say, the 16 megabyte large download, but you were right at the end of the buffer and there was only 1 megabyte of transfer space left, it would give you that megabyte and then 15 megabytes from the beginning. You'd split load into the two halves. Then when it goes to do the texture update, it would actually split update using the two halves as well, right? So crazy town. That's if we wanted to be super efficient, we would just do the extra code there because you totally could. not really worth our time, I don't think, in this case, because it's only for the end of the buffer. It doesn't really matter. So what I'm going to say here is we're just going to look at how much memory we have left before the end of the buffer, and how much memory we would have if we reset to the beginning of the buffer. If either of those two things is enough, we go ahead. If we don't, then we just say, no, you can't do it yet. You got to wait till some of the ops finish. Right? Very simple. So here's the size that we need. It's the width times the height times the pixel density, right? So when you do begin texture op, we're going to ask for this. We will maybe ask for more than that later when we need to start transferring bitmaps. So this could get more complicated. So we want to boil it down to a size requested because we want to be able to change this later. We're going to look at the size requested. We're going to say, first of all, if we look at how much memory we've got, we've got the amount that's used. So in here, we kind of have to say, we need to actually have, and we don't have here, how much total transfer memory there is. So what we want to do is say, all right, there's two possible ways we can load this. One is we can reset to the beginning of the buffer. The other is we can load from where we are right now. And so in order to do that, we have to compute a temporary set of values, right, in here. So what we need to do is say, well, if we were to load at the current location, then that would be here. And this is wrapped by this value, right? So, if we were to do this, then this right here is sort of a wrapped value. So, yeah, like you need to mod by whatever the size of it's going to be. You know what I mean? And we could make that a power of 2 if we had to, if this was like really heavy pressure, but it's not going to be, so it doesn't super matter. But anyway, so we do the memory at here. We say, look, whatever this is wrapped, that's where the memory actually starts. So that's the location. That means that there are sort of two sizes. If we start there, we know we can go to either first used or the end, depending on which of the cases we have. And if first used is in front of us or behind us, that sort of tells us which wrapping scenario we've got, right? So let me just draw that for you. So if you imagine that we have it in our buffer, we've got a particular point, and we've got a particular size, then the total amount we could load is either this amount or this amount, right? So we can either load this much or this much. But if instead, and this was the start pointer, so this is the used amount. If instead it looks like this, then this part is technically back here. Right? And so in that case, we can only use just the part that's in between. So we have two different cases to look at. One is if we wrap, and one is if we do not wrap. And I think those are the only two cases, right? So either we've got two, or we've just got one. That's my story, and I'm sticking to it. And so what we need to do is differentiate between those two cases, and we can tell which one it is by whether or not we wrapped. So what I could do is actually do it this way and say, look, if memory at is greater than or equal to the count, like meaning we've gotten to the point where we would have to wrap around. This is like the used space wraps around. Otherwise, So in the case where it wraps around, that's actually the easier case, because then what we know is it's just wherever we would have been, right? So then when we do the mod, right? So we do like memory at minus equals transfer memory count. So now we know like this, we know this location here, and we can just say the max size, you know, the max size in that case is just wherever the used space is being started minus where we're at, right? So that's where we're at, and here's how much we could do. Here's how much we could use. In the other case, where the used space is just one chunk, that means we have two spaces. So used space wraps around one continuous usable space. The used space is containing, so this is the used space is, you know, doesn't wrap two usable spaces on either side. So what we want to do there is say, let's get the size available by saying wherever the memory at is, we want to take the total size in this case, look at, you know, we want to look at that size. Now that we know how much available there is, we are ready to go. If, however, that's too small, we could instead try also the other one, which is starting from the beginning and looking up till memory at. So if size available is too small, so meaning this, right? Then what we can do is compute it differently and say, okay, memory at is actually going to be instead equal to 0. We're going to start at the bottom. And the size available is going to be computed this way. Know what I mean? Which actually it happens to be the same computation as here. You know what I mean? So that's fine. We could simplify this computation a little bit by just having the memory stop location be a thing that we pass out. I'm not going to do that. I think that's fine. It's perfectly legible the way it is. So that's how that would work. Right? So then we come down here and say whatever we know we did the best we could there. So if the size requested will fit, right? And I guess I could phrase it the same way as I phrased it at the top there, just to be clearer. So if we can fit the thing that we want, and there actually is room in the op queue, and probably I should do this in the other order, because honestly, why bother with all this work if there aren't any ops available anyway, right? That seems like a more sense way to do that. Like, don't bother actually spending all your time computing where to put this thing if you know you can't actually issue the operation anyway. So assuming we could issue the operation and there's room, then we're done. Now all we have to do is say, all right, go in here, get the op in question, get ready to fill it out. We know where the data is. It's just the transfer memory of the queue plus the location at where we want to put it. We know exactly where the transfer memory last used is going to be. It's just going to be this memory at location plus the total size that we requested. And that's it, right? That's the end of it. So unless I screwed something up, like that entire, which I probably did, but you know, hopefully I'm not missing anything major and we'll just be able to debug it. That entire thing is an asynchronous like texture transfer queue for variable size texture things that would just work and could be done multi-threaded if you wanted to. We don't have multiple threads that can issue texture requests at the moment. We just have multiple threads that can finish texture requests. But I think that just does everything, right? And it can transfer arbitrary size textures just fine. So then all we need to do now is say, well, all right, now we just, you know, when we set up these things, we do have one more thing that we need to do. Also, by the way, init texture queue is now incredibly trivial and doesn't require any memory either for the texture ops. Although what we probably want to do here is make it so that that we probably want to make it so that what's the word I'm looking for? I'm drawing a blank. Oh, we probably want to make it so that they can pass in what they're using for the transfer memory, maybe, or like how much they want. But I feel like we probably need to allocate it because it's kind of coming. It might come from the graphics layer itself. You know what I mean? So you can see why I'm a little like I think maybe you really shouldn't have it be passed in like that anymore. Yeah. So I think maybe we're just going to want to do something like, okay, you know, requested transfer buffer size. You know what I mean? And so then in here we would just say, well, you know, none of this stuff happens anymore. That's just not true. We go in here to the queue and we say, well, the transfer memory count is going to be the requested transfer buffer size. The transfer memory first used is 0. The transfer memory used count is 0. And the transfer memory is like some kind of something where we get graphics card memory, maybe, or we don't, or who knows what, right? The op count 0, the first op's 0, and that's all there is, right? So I think then if we look at what happens here, it's really just the transfer memory piece that's a little bit squinky. And so what we want to do is we want to look inside the OpenGL side of things here. And we want to probably supply that memory accessor in here. You know what I mean? So when you actually do the init texture queue, it would need some way of getting, like, it needs a way to access this. I'm going to go ahead and turn back on our renderer testbed. Because I think that'll be a good way to test this stuff out, and also we want to make sure that still compiles. You know what I mean? In fact, what I could do is I can even I can rem out even the game if we wanted to. But you know, at the moment we can just focus on this part. This stuff, DQ pending and NQ free, now go away. By the way, they're just gone entirely. They don't have to do anything. And so really what we're focusing on now here is like the OpenGL managed textures bit of things. And so in terms of getting like buffer memory to transfer this stuff, like I said, I don't know that we actually want to do that per se. We could later, but at the moment I think we want to just not take on that additional ball of wax, because that's a graphics GPU programming issue that we probably just want to leave till a separate time when that's the only thing we want to play with, is how to like most efficiently get those transfer buffers. So what I would want to do here is have a way that we can allocate memory that actually just works in terms of yeah, like in terms of how this texture queue is initialized. And it sort of needs to be able to thunk through. Like it needs to be platform specific potentially. Do you know what I mean? And that's a little unfortunate because it complicates that code, but like if we really want to be serious and say that, you know, you could go implement a serious renderer in here somewhere, I just don't see any way to not do that. Like you're gonna have to do, you're gonna have to allow it to allocate the transfer memory. That's just, it's not plausible to claim that this would be a real render layer if it couldn't do that, because you know that's going to happen on most platforms. So if we look at how the renderer gets loaded here, again, I think that means that the way that we were doing the texture queues, we vacillated a little bit with how we were doing the texture queues. I really think what that means is that init texture queue call is really going to have to move into the platform specific part of this, right? Another way to say that would be you could still do this, meaning you could still say how big this was and pass the memory here. But it really should be something that gets done inside the renderer side of things. So I think we can probably still do this, but I think we're going to have to... I think we're going to have to move this stuff into the platform-specific side eventually. You know, maybe not this part. This could be shared, but the actual... It would be a thunk, and the actual one would do a buffer lock around it, if that makes sense. And a buffer unlock here, potentially. So I think we're going to have to do that move, and I'm okay with that. But, you know, off we go. So I think init texture queue is fine like that now. And we'll like make sure we call that with more space. So like, for example, on here where we do init texture queue, so in here, we've got like text queue memory and whatever nonsense is going on here. Like, this is not what we want anymore at all, so that, you know, would go away. And this is probably not how you would want to do that either. You'd probably want to just get the pointer, you know, actually have an allocate, you know, you would get a texture queue out of this. And so when we call like Win32 init default renderer here and we get back the platform renderer, you know, inside that platform renderer, where is that platform renderer? So inside that platform renderer, I think, you know, I guess what I'm trying to say is I think what we're getting at is the texture queue is just going to be like in there, right? Like when you get that, you're going to get that back from Win32 init default renderer. And so, you know, it's not going to look like this anymore. It's going to look more like this. And I'm not sure... So inside Win32 Handmade renderer, we call Win32 load OpenGL renderer. And how does it actually allocate its memory? It just calls Win32 render alloc. All right. So I think that's how it's going to go. You're going to pull the texture queue out of there. You're not going to call this anymore. You got to get the texture queue out of the platform renderer. And so again, I actually love that. I mean, that's great. The reason I really like that is because if you look at what has to happen, now the users of the code don't really have to super understand what's going on there anymore, right? It's just kind of like, I don't know, you know, I know there's a texture queue and I know it's set up for me somewhere, somehow, right? Like, right? And so I think like the only thing we would really want to do there is maybe pass down how big we want that to be. And so in here we would say, oops, something like, you know, when we do max quad count per frame, you know, at the end, maybe at the end of all that, we would say like the texture transfer size. So handmade texture transfer buffer size like that. And then, you know, who knows, I don't remember where we specify that stuff. It's just in Handmade platform. So in here, you know, these, yeah, these can be things that are going to be set more dynamically in the future. But so I want them passed through because they're not going to probably be pound defines forever. They'll be something that's a little bit more dynamic. So, you know, I don't know, maybe we say that there's, you know, a pretty large amount of texture transfer space for now because why not? That would allow us to transfer 64 sprites per frame, which seems maybe a little low, but you know, maybe we want more than that ideally. I'm not sure. Maybe we want to do more like 128 sprites per frame optimally. Again, The bandwidth to the graphics card, I don't really know what the bandwidth of this graphics card is anyway, so I'm not sure what's realistic to expect there. But either way. So anyway, that's all well and good. Everyone's happy and smiling and everything's great, and you know, little kids are dancing around and all that stuff and whatever they do. And so now I want to be able to pull out that. So when we actually have the texture queue, right? The texture queue goes through the game memory there, and we do the process texture queue. The thing I like about that is you don't have to call this anymore, I don't think. So in other words, this call goes away too. So I think all you have to do is pass it. You don't have to call that function. That's my argument anyway. That's what I'm going to claim. And so you really just have to go, oh yeah, the texture queue's in there somewhere. That'll be whatever. I'll do that. It's great. It's good. No one cares. And that means like in the code that, again, like if we take a look at our usage code here where we do like texture queues and stuff, that now doesn't have to actually happen. So again, it's really great. It simplifies the texture queue entirely because we don't have that problem anymore, right? So this stuff, process texture queue, can just not happen, right? Ever. It just happens automatically. And I think that's much, 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 much better, right? So I love all that. That's all really good. It also means that up here, right, this stuff gets simpler now. We don't care about that. And so we've got the max texture count. And we also have the texture transfer buffer size. And, you know, who knows what that is. But in this app, it's probably smaller, right? Who knows? And so texture transfer buffer size. That all looks good. And then we don't have to do any of this. So again, it just makes our render even better because now it's like all that stuff that you were worrying about before. Not only can it now be done on the hardware side if you want to, so we can lock memory that's actually aperture mapped properly, but you also don't have to know about it. So anyone who uses the renderer is just free to have a party without ever even knowing what a texture transfer buffer is. And the only thing they really have to do is have some idea of how much textures they're trying to push through it per frame so they don't set this number too low. Right? That's all they really have to understand. And they don't really even have to understand that if the default values are set particularly well, you know, then it should be fine. Right? So that seems pretty good to me, and I think that just makes everything better. So I'm a huge fan, and I claim that that's what should happen. Now, when we actually are in OpenGL here and we go to do our manage textures, we want to do the manage textures probably like on end frame before we do anything. We'll try to kick off those. Ops. So OpenGL allocate texture, you know, does this bit right here. I'm going to say let's go ahead and bring that in. I don't know why that's outside. I don't think it really should be. I think we probably want that in here. Because this all has to happen together. It can't really be spread out, if that makes sense. Yeah. So this isn't gonna work this way anymore, because remember, we don't actually have a linked list anymore. So we know that this is what we want to do on each individual texture as we spin through it. What we don't really understand yet is what we need to do to actually process the stream. I'm gonna put that aside for a moment and just say, when we do OpenGL manage textures here, inside end frame, I'm gonna do that automatically. So when we come through here and we do it, after we process the change to settings, we're going to kick off any texture downloads we can, right? Because we know we're going to need them soon, possibly on this frame, but not necessarily. So we want to go ahead and get that queue going. What I don't remember is the OpenGL part of things. What is that? Is that just OpenGL? Yeah, OpenGL. Yeah, this right here. So the platform renderer here, it's got it in there. So I think it's to get the queue, like again, you don't even have to pass it in. It's just here. So there's the texture queue, problem solved. And so every time here we can just like kick off our textures before we go to actually do anything else with the actual render buffer. And we can change the settings first, so if we need to reallocate texture buffers, that'll happen here. So when we do OpenGL manage textures, now we need to do is we need to actually have some, maybe a utility function probably in the renderer side of things that can get, as we go through, that can get our ops off in a way that's easier for us to work with. Right, and so what we want to do is in here, when we dequeue one of these, we want to do the right updates to these transient values to make them still be consistent. And so that's really what we're trying to do here when we do the dequeue. So what we know we want to do first is just say, look, we're only going to run this thing while there are some ops in the queue. So the very first thing we can say is just, don't do anything if there aren't any ops in the queue. Because that's a totally valid situation for us to be in. We don't know that somebody asked to download textures. So the op count may be just 0. There may be no ops at all. So if there is an op, then that's when we would start actually looking at things. So if we wanted to look at what was going on, we would say, all right, there's a texture op. The op in question that we're going to look at first is going to be the ops array plus whatever the first op index is. So we get that one out, right? Now we need to see is, can we process this one, right? Can we even process this one? So we look and we say, well, okay, if we look at and see what its state is, we want to look and go, if it's empty, then we would skip it, right? So we kind of want to have this part of the routine only occur if we're actually saying it's time to transfer. Right? So if this thing says ready to transfer, we want to actually send the data down. If it doesn't say ready to transfer, then what we have to do is say, well, what if it said stop, right? What if it said I'm not actually loaded yet, so I can't actually tell what I should be doing here, right? And if that's the case, then I can't advance any further, right? I can't do this actual op. I think we want to check that first. Meaning if we can't, then we just break. Otherwise, we look to see if it's ready to transfer. And if it's ready to transfer, then we do the transfer. If it's not, that means it must be empty. So we can actually assert here that it's empty. Because it's not either of these, it has to be this. I don't think there's a race condition there because you can't set something from pending load to empty or from ready to transfer to empty. So if it was empty, I guess, well, no, that's not entirely true. No, okay. The only thing it can do asynchronously is go from pending load to ready to transfer. So it's got to be one of these two, always asynchronously. So asserting for this is always valid because the only thread that could have set it to this is us. So we know we aren't setting it behind our backs to empty. So I stand by that. If we moved this to be completely asynchronous so that multiple threads could be requesting textures at the same time while it's doing the texture retirement here, then it's a different ballgame. But that's not what we do. The only thing that we do asynchronously is move something from a pending load to a ready to transfer. That's it. So as long as we make sure that this ready to transfer thing is at least a little bit fenced. Do I have any other of these? Yeah. So as long as I make sure that I don't actually read these out of order, we're probably okay. So I think that probably should be fine. All right, so in here, I think that's all good. And we issue the transfer. I don't even really know if I need this, because if you ever could have gotten this in the first place, then when you go to actually use this, it's the data pointer can't be stale. So it's actually the other, in fact, I'm not even gonna bother with that. Because if you think about it, all of this stuff, that data was set long ago, long before we even issued the read. So this, it's only the GPU that would have to worry about the data being stale in some sense, right? So forget that. You're not gonna do that. All right. So all of this transfer stuff works exactly the same way that it does. So the only thing that we now need to do in here is we need to make sure that when you are either, like when you pending load, we stop, we don't go any further. But when we transfer or are just looking at a null op, then what we do is we have to actually move these around, right? So that's the big part of the circular buffer. So when we want to move them around, what we have to do is say, all right, first of all, we're going to take the op count and we're going to decrease that by 1 because we did retire an op, right? We did move past 1. We're going to increment the first op index because we are moving forwards. And then if that first op index is greater than or equal to the total amount that we have, we're going to reset to the beginning of the list. So we're going to bop backwards and go back to the very first op and start, plowing through them that way, right? So we go off the end, come back around. So that's a pretty easy way to retire the op. That is, I think, just done. Like, I don't think there's much else to worry about there. This part's more complicated. So now we have to do is worry about the transfer memory, because now we have to move the transfer memory forwards to coincide with where it should be based on retiring this texture op, right? That actually might just be trivial because we set ourselves up for success by saying each texture op just remembers where the end of the memory it needed to use was. So we can advance this forward. Now, granted, if you look at what happens here, really what we would need to do is set up what's called a fence on the GL side of things if we were using a mapped buffer. Since we're not using a mapped buffer, the copy occurs here from our memory to GPU aperture space. That CPU to CPU copy happens here, which means we can immediately free up the memory right now. We would probably add another tracker in here for fenced memory transfer so that in the future we could overlap those transfers better without a copy. We're not going to do that now, but if we wanted to make this more efficient GPU-wise, we would be looking at that. All right, so I think that in here, once we retire this op, all we really have to do is say the transfer memory first used now becomes transfer memory last used of the op, right? And so the only complicated thing here that we've got to do, and it is a little tricky, is we want to be able to reduce the total amount of memory used by that. Now, maybe I should just make things easy on myself and just say transfer memory count here. And so then if I did that, I could just do this. I'm all in favor for making it easier a little bit there. Yeah, we got to store an extra U32. No one will care about that. There just aren't enough ops as compared to the footprint of textures that they're actually transferring. So it's like, don't be penny wise, pound foolish there. It ain't going to make a difference to our footprint at all. So that's going to be totally fine for now. So in here, what I'm going to say is, look, I'm just going to say transfer memory count in here is just going to be that size requested, and then we're done with that, right? I can also assert here that this is within the range that it should be. So I can say, I really want to make sure that that pointer is, less than one of these the transfer memory plus the transfer memory count. Like basically, like when you actually complete one of these things and are ready to queue it off, let's make sure that we're not passing totally bogus nonsense here. But I think that's basically what we want. So this right here, now we'll just do all of our texture transfers and off we go. Again, no need for free lists, no need for any of that stuff. This is all off the queue, so I gotta go ahead and throw a Q star on there. I don't know if I got them all. That's not going to let me do that, is it? That's fine. I could do it like this. Right? Just verify that the memory at is within there and the last memory used is within there. Like nobody wrapped around. Like it's all good. Yeah. All right. Let's keep on trucking. So we got our state here. This is on the op. What else you got for me? So when we call a knit texture queue here, someone's going to have to actually do this work, so that's a little bit squinky. So in here where we do a knit texture queue, that's going to have to be routed properly, like so, in here when we actually do one of these render allocs, we would have to do the init texture queue in the same way. And the pointer to process texture queue can go away too. So actually also, this gets simpler, right? That is not a thing anymore. So it's really only begin and end frame. So yeah, this just keeps getting better. If you think about it, it's pretty great. Now it's literally just those, So that's just fantastic. I'm just loving how this is coming together. It's very, very satisfying. Okay, so in here we've got render texture queue. We know we've got it, so because we know it's just this. But we need to initialize it, and so what we want here is the requested the requested transfer buffer size is actually something we're going to have to put in here, and we need to actually allocate that memory. So it's really just going to be this. And in the future, like I said, we can maybe do that a little more cleverly and actually get buffers that we specifically want there. But now I'll unwind those calls and make sure that these we don't need that. And make sure that everyone passes the right stuff. So init texture queue is now in that unhappy place where that's like a thing that's again part of sort of a it's in a weird place, but I'll stick it like so. When we do the load entry, this is the texture transfer buffer size that goes in here. So that Win32, that Win32 load now has that in it. and it gets passed through here. We should really consider bundling those. You know, when you look at it now, it seems like that should be a bundle. While I'm in here, I may just bundle them. That seems, you know, better. Because now you just look at all this stuff that has to change. Why bother, right? Why not just go up here and say, look, the parameters for this system go in a struct. So in here, when you're going to call one of these, there's something like this, or that, you know, and maybe limits, something like that. And all these things just sit in there. So now, you know, you just pass one of those along, and we don't really have to deal with it anymore. Like, all of these things that do pass-throughs, they don't have to keep changing, which is, you know, nice. They just pass through that, and then if things get added to that, then it gets passed through automatically. Right? And that seems a lot nicer to me, certainly. All right. Okay, so I think that's just going to create some typing for us here to actually put in that change. But other than that, I think we're in good shape. Oops. All right. So platform renderer limits. Okay. So yeah, let's see what else we got here. So we need to change the way that the textures are getting submitted in here. When we initialize our test scene, we need to submit those textures. And you can see here, we need to actually do the operation, the new way of doing the operation. Which thankfully is very, very simple. So really all we have to do is say, I would like to begin a texture op, please. Here is my texture queue, which is texture op queue. And then I will tell you how big it is, like so. I will then set the texture handle, but the data is already set on it, right? So in here, we don't actually have to do any of this. We would just say complete. You know what I'm saying? Yeah, so this actually I think that means we don't have to allocate anything here either. So actually this yeah, this would just work. We can write directly into there if we want to. So what we can do here, right, you see the pixels, we do this nonsense. So, you know, it's too bad we have to do a copy here because we could maybe just load it indirectly. But I'm just going to do this. So here's what I'm going to do. I'm going to take this. We'll just stick that there. And, well, I guess actually... I'm going to call that the result. And I'm going to say... I'm going to say all of these things... because we don't actually need to return those. I'm going to change the way this routine works a bit and just say once we get down here, we can actually, yeah, we don't need the pitch or any of that stuff. So in here, we can just actually do the texture out properly. We can say, where was that begin? Did I accidentally delete the begin? That was not smart. There it is. So in here, yeah, I'm just going to say, let's put this stuff right here. We'll actually make this copy into the texture queue. We will refer to the texture here. And I think that's all we really needed there. You know what I mean? Then the destination will be this thing. So the only thing we want to do is make sure that begin texture up, if it fails, we don't actually try to complete the transfer here. I don't know if we've got error reporting. And again, that can't really happen in this test code, but just so people who were looking at the test code didn't think they could just count on the op coming back properly. That's all. So I think that's all good. And so in here, instead of source dest, what we want to do is actually have an actual dest. I don't know why that looks like that, but you know, it would be like this. So, you know, we would look at the source, and then we would have the dest like so. And I think that's really all there is to it. Right? Now, why we're using uint instead of... I don't know why we don't have those as our standard types here, but I guess that's just the way the cookie crumbled. That's all good. And so, yeah, in this case, texture op result just needs to always be returnable there, even if you didn't get one. All right, so renderer test is now good to go, I think. So I think that means we can go ahead and try debugging that method of texture transfer, just so we know that it is working at all. You know what I mean? We can switch to the renderer test app here and debug build as well. And then this is kind of nice having the test bed because it means we can debug in a much simpler scenario than we would have had to do otherwise. So this is great. Now we can go see like what's going on with the texture transfers and why are they broken and whatever else is going on, right? So we'll start there. Let me just see what's up. All right, so we can't really tell anything by that. Let's step in and watch the texture transfers fail and where they fail and how and so on. So we can get some kind of an idea of what's going on. What is that little... Does that just mean that's the start of a function or something? Okay, great. Can't wait to see what's in there. So I'm going to go ahead and let's see, jump to something good. Where am I? Where's my load BMP? Okay, here we go. So I'm going to jump down here. I want to look and see like just the basics, you know, just get everything in here working. So first of all, you know, did it even get initialized, right? So looking at the size of this, I don't remember what we said for how big it was supposed to be. What did we say? Did we say this? I'm hoping. Is that what we said? No. What did we say? 16 times it? Maybe? What did we say? We'll start there. What did I actually ask for? I don't even remember. Oh, I'm in the wrong file too. There we go. So I just wanted to see, like, I don't remember what we asked for the texture transfer size, and so I want to make sure that that's actually getting set properly. So that doesn't look right. So I think we're already a little wrong. So I'm just going to step in here. So if I look at the limits, that's the number that I was expecting to see. So this is the numbers I was expecting. Let's jump in here. So if we go into init default renderer, you can see us grabbing the actual renderer that we want here, and then we jump in here and start the initialization of OpenGL. So we've got the texture transfer buffer size. We're passing that in both cases. So I'm going to look in init texture queue there, and I want to see what's going on. So here we are in the transfer queue. So we initialize that properly. That all looks right. What did I do? Did I... So this doesn't properly increment the used count, does it? So the queue, in this case, we add an op, but we don't actually add the memory. So this actually should be queue transfer memory used count, right? That should actually go up by the amount we used. I think everything else can stay the same, but that can't. Right, because this stays in the same place. This has to go up. So I think that's correct. So we advance by that size that we've requested. So I think that's what we want there. That looks fine to me. But what I'm not sure about is then on cleanup when we come through here. That also does look okay. All right. So now I want to rerun through here and because that was wrong. But again, so after init texture cube, I'm gonna jump in here. Just want to see what's going on. So there's the queue. It looks good. And if I look at this, I just want to see what's up. Getting all our functions, the old OpenGL party. So that all looks pretty good, actually. We come down through here. Let's see what the renderer thinks of things. That all looks right. So it looks like we're starting off good. We try loading a bitmap here. So, now we're going to come down here. What's the texture op queue have to say? That all looks good. So now we can get started. All right. So can we get an op? We should, because we should have all of our ops free. How much do we want? We want that much size, right? And so now we got to see how much we can actually get. So we look at where the memory is. Memory's at 0, right? Because nothing's used. So now we have to see, is the memory at higher than, would it have wrapped, right? And the answer is no, correctly. So the size available is like the full size of the transfer buffer. So that's actually fine. That means we can do this if we want to. So the size available and the size requested. Oh, that's backwards. Well, that answers that question. That's how I wanted to write it the first time. I don't know why I didn't do that. I was like, oh, we should keep it consistent with that. But that's a different check. So let's try that one more time. So we find that, yeah, we can actually use this thing. So here's our op index. It's 0. Now the op count should be 1, and it is. We then come through and say, all right, we've got a result. So this result is the one we're actually going to fill out, right? Here's our texture transfer. So we set the data equal to point to what should basically be the transfer memory, right? It's the base of the transfer memory, yep. We say the amount is however that was. The last used is going to be that same value because that's where you would move to afterwards. I think that's okay. Set it to pending load, which it is. We use that much of the memory. We then assert that everything's okay. In this case, we got the op loaded properly, so we pack the texture in there, and then we complete the op. That's just doing the copy. Complete texture op just kicks it off. It says it's ready to transfer, and so we're all good, right? That should just be that. Then when we go into, the actual rendering code, what we want to do in there is look and see when we do end frame, which is here. Let's make sure that the renderer actually does that stuff properly with the sending the textures down. So here's the manage textures call. There should be one for every texture, and there is. We come in here, we grab one off. This is it. We should also look here, and we can see how much is used. Blah, blah, blah. So in here, we look to see, is it pending load? What is it? What have we got here? Well, they all should be ready to transfer because this ain't asynchronous. So everything should be loaded. So we should hop right to this case, and we do, so that's good. There's the data we're going to transfer. It's not a special texture because it's actually small enough. So we drop it down. And then the question is, like, do we handle this right? So let's see. So the first thing we need to do is we need to reduce the amount of memory used by the memory that we got here. And so that looks like it worked properly. Then we need to move it up to so that the first used is now past that, right? And that we do. We reduce the op count down and we move the next, so we'll be looking at the next op. And then we just look to see whether or not we've wrapped. And in this case, we definitely have not wrapped, right? So we haven't actually gone over the total of the array. So we can just keep on going. We keep doing this and it should just work, I think, right? And at the end, when we're all done, when we get to the last op, we're looking at the op count. There's 2. And here's one more. And now that we're done, when we look at the queue, we should find that there's no memory used, right? And that's accurate. So that looked good. And hey, if we look at this, that looks great. It looks so hey, good. We only made one mistake. that is the only thing we screwed up. Would have worked first time. What are you gonna do? So that looks like the renderer test. Everything in there just looks totally fine. So I think we don't have to worry about that problem now. So the next question is, what if we tried to stress out the system a little? So, there's probably bugs there in the wrapping. So what if instead of giving it the easy case, what if we said, hey, you know what? You only get 3. Well, it can't really do the wrap because we don't call process textures. So we can't transfer that. But instead of the transfer memory here, yeah, I guess we can't really, I'm sorry, I can't test that here. We should create a test case for that here because it would be easier to debug it. But yeah, you can't really, yeah. We can't really test that here in a meaningful way, so I guess we just won't. We can do that later. Okay, so now we can take the game code, and now that we have the different texture transfer stuff set up, now we should be able to make this the asset system. We should make the asset system work with that texture transfer code, and that shouldn't be too hard. We can stub out the sound stuff for the moment because we updated both of them, and then we can do the sound stuff in a separate pass. So taking a look here at loaded bitmap, we know we got rid of that, and so this stuff that's happening here, again, really just not necessary. So we can kind of just ignore it. The asset itself has the texture handle in it. You know what I mean? So it really looks more like this, if that makes sense. We don't need the loaded bitmap interim anymore. In terms of the size of the read that's happening here, the read size is just going to be whatever the bitmap size is in total. So I think we could also just make the op. We could use the op to give us that back in a sense. I don't know that we really want to do that, but we could. Meaning this right here has already computed that. But I'm not going to do that because the read size could actually differ from that in the future. So instead here I'm just going to say, look, the read size is going to be bitmap width times bitmap height times 4, because that's what it actually is. Texture out memory in this case for destination, it's just data, it's not memory. We changed the name of that. The finalize operation parameter is not a thing anymore. That went away. And so now inside load sound, what I'm going to do inside load sound is just say you can't load sounds anymore. And then we'll come back in here and we'll implement the sound loader in a cooler way. And that'll be the end of it. Okay, so when we do a load font, we need to actually get the asset in question here. It looks like we're just proceeding under the assumption that we already accessed it, but we definitely didn't, right? And so that needs to be put in here. Yeah, there we go. Acquire asset memory. Again, not really necessary. So this is a different, when we're doing asset memory allocations here, these are things that I don't think we ever actually have to worry about multiple threads pulling on those at once. So I think what we want to do there is we want to, by the way, how much time do we have? I don't really know how much time we have. I might want to take a quick break and come back to do this because I might want to spend another hour on this. I can't decide. I think I might want to come back to this a little bit later, but we'll see. Like, because I don't know if I want to spend another hour on this, and if I do, I might want to take a break and refill like my waters out and everything. Yeah, let's do that. I don't want to rush this part because we're about to do the rest of this. So I'm gonna say let's take a quick break, and we'll come back. So I'll start up the stream again in a second. I'm gonna go ahead and stop the recording. Okay, we are back. We have had a snack. We have refilled the water. We are good to go. We are not in dire. Our voice is not in dire need of hydration. Dihydrogen monoxide. We have increased our dihydrogen monoxide take. So that's good. All right, so acquire asset memory in this case is just a situation where we have font data and we don't really want to load all of the font data that we have. So even though font data doesn't really need to get evicted because it's small, if you imagine a case where you have 30 different fonts because maybe you had lots of language localization, you don't want to load them all. So you still want to actually just be careful about how much you're using there in the non-restored memory pool there. So we don't really need acquire asset memory, I don't think. We can pretty much do a direct push. So we can pretty much just say, look, give us this much out of the non-restored memory pool, and we'll just go from there. So I think that's good enough for the fonts, because like I said, we're just going to load those at the outset for the ones we actually care about, and then be done for a given situation. We can get fancier and allow eviction of fonts in the future if we really find that we need to, but for the moment, it just doesn't seem relevant. Okay, so yeah, in here we're just getting rid of the concept that we had the work asset stuff to begin with, because now we just don't have that happening anymore. In here, I guess I'm not sure what we would do in the case where the font doesn't actually get loaded, other than give the memory back. And so, we could try to be a little bit better behaved there and just say, well, when we want to be able to mark the location. So in the future, if we want to rewind back to it, we could do so. So looking at, at how that works, you can see it doing the rewind here. And we kind of have this temp count. So what we can do is say, let's pretend we're going to start a temporary memory block like so. So we just say, yeah, memory point, begin temporary memory. So here we can just say, look, we're going to try to do some stuff with this memory. But, if we fail, then we will rewind it. So, end temporary memory, we will do here. So if we can't actually get the font set up, then forget it. We'll unwind. But if we can, then we will try to load it, right? So that's really all I wanted to do there, is just make sure that that path works okay. And we won't set the asset state to loaded unless we were actually able to do it, right? So we'd do this. Again, this is synchronous, so it's not a big deal. So in the case where we actually can load it, what we want to do is say, like, you know, hey, you know what? I decided, actually, so, you know, just kidding. I would like to keep the temporary memory going. I changed my mind about that. So, you know, sorry, but it turned out that I really liked the memory so much, I'm going to keep it. And so there, all we have to do is just not do this, right? All we have to do is just say, all right, the temp count goes down. We can assert that the temp count is greater than 0. And we can also do this, which is to say if there was any in the first place. Now, the temp count here, it seems like this temp count greater than 0 really should have been like that, because if you're going to subtract away, you'd better check. So I'm not sure why that wasn't happening in here. So really, we're just doing the exact same thing, right? But we're not doing any of the actual clearing. So that would allow us to give the memory back in the case where like the file read fails, because file reads can fail, right? We don't know that it's the file read's going to succeed. And so in this case, I think we want to keep it working properly. Okay, so that was all I wanted to say about that. We can get the font here, so that's all good. I don't know what else has to happen here that we're not doing. Yeah, asset font. Ooh, that is loaded font here. So what am I actually doing with the font? Oh, we're just looking at the glyphs in here. So in terms of this part right here, I feel like this can really just be blocked off. The font glyph stuff, where we do the load, I'm trying to think of what I really want to do there, because I do want to get it to load. So maybe I have to actually literally call that HHA font. I don't know, but you know, if we look in here where those two things are happening, oh, duh. It's the same font. I don't have to do anything. So that all looks pretty good to me. Inside allocate game assets, this stuff here is going to have to change a little bit. So there's a couple things that we're going to have to do with, because remember, we weren't tracking free texture handles before. We're going to actually have to do that. And so, yeah, like, you know, there's a couple different ways we could do that, and we'll have to decide exactly how. But the rest of this code can go away. If I go into the audio layer and we look at the get sound situation here, so we're not going to be able to do get sound anymore, but almost everything else in this code all will work. The only difference is that when we go to get the samples don't come out of the loaded sound anymore. So it's actually the samples that you get back. And the info for the sound comes like out of this. So there's an HHA sound here, you know, and I know I could do it this way, and you know, whatever, you know, this kind of thing, right? So when we actually get the sound samples back, we're going to play those out of here. They're not going to come out of the loaded sound anymore. Everything else, though, will work. So this is just get sound info, right? It's just this. And so everything else would work just fine. And if we need to actually get those samples now, the only difference, right, when you look at what we're doing all throughout all of this stuff, is when we get down to the very end and we want to actually mix something, then you're going to want to go and you're going to want to go and use that sample buffer there. So if I look and see where are we getting that from, loaded sound. Yeah, so you see that loaded sound samples and the bracket nonsense there. Right, you can kind of see all this happening, samples. I don't totally understand why we're using a bracket 0 there. Was this code like somehow looking at something for 2 channels and then only did the 0 sample here? Like, I don't know why I don't know why it's really written like that. You know what I mean? Let me take a look. Because, excuse me. In terms of what that returns, I don't see why we would have done the channel pointer that way. Let's just take a quick look. So inside the asset system, when it was actually going to go do the sound load, so in this code, which we if-zeroed out, but that still exists, right? So in here, you can see when we get the memory, we're setting the sound sample pointers so that they're strided along samples. So I guess what I don't know is what were we planning to do there? Like, I mean, this never appears to do the channels differently, does it? Like, if that's the channel index, well, it's only ever set to 0, so it's not exactly doing a very good job loading binaural samples. So I'm assuming that, oh yeah, and there's a handle stereo to do right here, right? So this is actually just nonsense. And we can, you know, we can fix this code, I guess, later by just calling it twice in a loop. I'm not sure why we didn't do that, so, you know, I guess that doesn't matter at all. But point being, when we call get sound and we get a sample handle back here, we can, if we want to, we could actually imitate, excuse me, we can actually imitate what's going on in that loaded sample. We could do that if we wanted to pretty easily, actually. We could keep the loaded sound, and when you actually return the samples, you could return them in that. So, you know, we could do loaded sound and actually have, you know, something like this where we actually do have that block of pointers there, and you can use them. It seems dumb because it's not like you don't know where the memory is. So I feel like I'm just not going to do that, because since we can always stride based on how big each individual channel is, at most what I would do here is return a channel size. Like, at absolute most. So I would just say this is just going to be this. And that's pretty much the end of it, right? Like, I'm not going to do any more, you know, work than that. And we will just advance the sample pointer by the channel size when we go to do the next one, because it just seems dumb to do anything else. I mean, it's a fixed size thing. There's no, it's just silly at some level to do anything else, I would argue. Okay, so again, like, we're getting down to like very few actual things here. What is it? Get sound samples is the call now, right? Yeah. So we're getting down to very few actual things that have to happen here. Now remember, we changed this to say that there's platform render limits now, which is just a more convenient way of passing this stuff along. And so all of this stuff that was sort of being passed piecemeal before is going to go in here. And that's just to facilitate the fact that this is like a conduit problem, right? You've got sort of a bunch of things that are getting passed through several places, not because we would really want that to happen, but because we have to go through gyrations for dynamic loading, right? Because remember, we've got the renderer is actually loaded out of a DLL so that people can swap in different renderers if they want to. So we really don't want to force them to have to update that if we decide to conduit more stuff through there. So we really want to just fill out the limits now from from the parameters exactly as they were before. If I go into the renderer and look up those differences there, I've got the max texture count, and I've got the special texture count, and the buffer size there. All of that stuff seems pretty good. And let's see here. Yeah, we're down to just a few things. The sentinels are not here anymore. We don't need insert block, assets, sentinel. None of that stuff is here. All that stuff can be removed. So yeah, looking through here, we can just visually just inspect that there's no more of that stuff still hanging around, because we don't really want it. It's not useful. So then we're left with just a very, very few things in here. So you can see we've got update here. We're trying to send out a single pixel texture. That's our fallback white pixel texture. And that's just there. The only reason that's there is because we kind of have this fallback case of non-textured things. And the question is, is there a better way to do that? Do we want to do that in some other way? There's probably things we can do. But I'm going to leave that as it is right now. I'm going to let that just go through the normal process that it would go through. And we'll go ahead and let that op actually play itself out. So again, if we want to do that, it's, again, really simple. I like this API a lot. I feel like we've done a good job here. Getting down to something that's pretty straightforward. So if we look at our renderer test bed here, we actually did basically what I want to do down in here, right? We just did a really simple thing where we said, like, let's make sure we can do an op here where we set this up. We're going to require that it be completable, but that's about it. So the assets white pixel pointer, that's not actually got, like, it's kind of nice here. We don't really need these anymore. It doesn't need to be stored because we can write it into the op itself. You know what I mean? So we can make this texture op stuff a little cleaner as well. So we can just say, all right, the op data is just going to be the white pixel, and then we'll complete it. And that's it, right? So this doesn't actually have to happen like that anymore. So now I think we're in a position where we're more or less doing the right thing. But now we got to go debug it, because remember, we stripped out a ton of code there, right? This just got like way simpler than it was. And so when we're looking at like what's happening here, there's a lot of things that we could have screwed up in there. And so we want to go through and actually make sure that we know at all what's going on. One additional thing that I would say here is this could stand to be a little bit more systemic at this point. When we're actually going in and doing the texture handle stuff, this bitmap width and height is really should possibly be set by the texture op call itself, just to make sure that people don't accidentally set the width and height wrong when they're doing that texture handle usage. So I feel like there's probably a little bit we could be doing there that would clean that up, and I might go look at that. But first, before I do anything else, right, I just want to get that basic, the basic first pass debugging done, clear out all the failure cases and whatnot, and kind of go from there. Okay, so let's see what we started off with here. We've got an assert texture empty. Nice. That's a pretty good assertion. I guess we just thought we'd assert just a flag because why not? Yeah. Okay. So that's pretty funny. Where's our OpenGL renderer there? There it is. So I don't know what I was thinking there. That's not what I meant. I meant that, right? So let's try that one more time. That was pretty silly. All right, so let's take a look at what's going on. Here we're in update and render entities. We're getting a bitmap ID. Okay, so here in this case, the bitmap ID is 0. We probably want to handle that case, meaning in here, if the asset that you ask for is 0, we probably don't want to get. We want to give you back the null asset in all cases. Now, I don't know. Yeah, like. It seems like, in some sense, it should be possible to always count on that. Like, I'm just trying to think through in my head. If this asset is always set everywhere to null, then the texture handle will also be null, so it's fine to return that. So this assertion, what we probably can do is just actually allow that case just fine. And what we would want is, like, when we do this assertion, assert that either the value is 0 or that it was a bitmap, because anyone is actually allowed to get the 0 value out. So, you know, it's more like this sort of a thing. So I think that's fine. You know, famous last words, but I think that's probably okay. All right, so now we want to actually debug like what's going on, because now we're actually running straight through okay, but we do need to make sure that when we trigger our asset loads, they actually get loaded and somebody will actually like download them, right? So we need to make sure we actually have that whole pipeline flowing properly. So if I drop into the asset code here, what we know is, you know, we know where we're kicking off an asset, and we know where we're retiring the assets. So this inside load asset work, right, which is the callback that's happening on async that waits for the read to complete, and after it's complete, you know, we head in here and do the texture op retirement. So we know that that code path needs to get hit, otherwise we won't ever download the texture. We also know that our load bitmap code has to get hit, or we won't ever load the texture either. And so what we want to look for is this code path working properly. So we want to come in here and take a look and see what happens. So here we're trying to load a 512 by 512 bitmap. And we want to make sure that this all works properly. So when we come in here to the 512 by 512 case, we want to see that we actually do get an op. We do get an op, and that op is going to be in the pending load state, which is exactly what it should be. And then when we come through here and we start up the task that we're supposed to kick off, what we want to do is set up that texture handle, right? So we should now see an index and a size. That looks, you know, like roughly correct. And then when we come through here and we start the, you know, we get that asset work out of the tasks arena here to actually start this task going. We set up all of the pointers and it looks pretty good, right? Like, you know, there's the load. It's happening in the right spot, it looks like. The texture op's getting set, the queue is set. We're gonna stuff it in the low priority queue for being handled later. You know, that looks fine. So I guess what I would say is that, you know, that doesn't look too concerning. What about this? Is this maybe where stuff's not getting set properly? I don't know. So here we've hit the completion state. We look at the texture op. We're gonna step into complete texture op, and all that does is it say, hey, this is ready to transfer, right? And then we also double check the sizes there. So you know what? There's one thing that's not really right here. This would have to do a cancel if it didn't do a complete, right? So that actually has to be moved down here in a sense. I mean, I don't even think in a sense. I think it just has to be moved down here. That's not what's failing now, but that needs to happen. We set the state here to loaded, and I feel like that should have worked. Right, there's the offset in the file. There's the size. There's the destination. That all seems reasonable. So those states are loaded. So, that seems pretty good. I'm not sure what the problem is. It might be in our buffer reading code that has somehow, it stalls out and can't make forward progress. So we can go take a look at what's going on in there in a second. Before I do anything else, though, I really don't think that piece of code is correct. So, even though we're not really testing or trying to work on this part right now, I don't actually want to do this. I think what I want to do here is this. And so what we would say is, I think probably here, and then this, probably. So if we were unable to actually get it, we're going to clear it. We'll just send down a 0 texture, and we will set the state to load it even though it failed. We could choose to regress and set the state to unloaded. I don't know how squinky that makes us, but we certainly could. So we could say something like final state. Like this. And we can say, look, we're going to assume that we regress to unloaded, and then if there were no file errors at all, then we'll say that we regress, that we progress up to loaded. We can do that. The thing that I'm not 100% sure about is, again, how we're going to exactly manage the idea of which texture handles are free and which texture handles aren't free. So that's going to be a more finicky process. We'll have to, we'll cross that bridge when we come to it. So I'm going to step through that one more time just to make sure everything's kosher there. So, there's us reading the data from the file. Assuming that there were no errors, we're going to set the resulting state to loaded. Otherwise, we'll regress it back to unloaded. When we do our complete texture op, that will set the state of the texture op, and then we'll set the state of the asset at the end, and off we go, right? Now, what I'm not sure about, like I said, is I'm not sure about the thing where we're actually, okay, we're already in debug mode, so that's good. I'm not sure about where we're actually going to peel those off. So I'm going to look inside, went through to Handmade. I'm sorry, actually just Handmade OpenGL, just the OpenGL render part of things. I want to see what's going on in here. I want to know what's up with that. So when we actually get an op count here, when we get a ready to transfer, what's going on. So if I look at, what's the texture index? There's the texture index 0. This should be that white texture that we specified in theory anyway. Let me verify that we're actually getting that. Well, you know what? I don't really care about that, I guess, now I think about it. Let's just look and see what happens on the next time round. So we know we actually filled all 128 elements of the queue on the first frame, right? So we had tons of textures coming in. So we're stressing it in a way that we don't normally stress it, right? Or that we didn't in the test app is all I mean. So when we get something that's ready to transfer, let's see now, we keep going. What have we got here? What's our texture? 512 by 512. That's like that first one we saw. It's not special, so it's going to just look at which texture it was. It's going to update that. I don't know. We should probably look at the data pointer. Oops. Is it good data? I don't know if there's a way. This can't view images unless you install a plugin, hilariously. I need Nick Slivka's debugger. That had image viewing in it and stuff like that. Remember, it was awesome. Anyway, so in here, that looks, okay. So I'm not 100% certain what the issue is because I'm not seeing an immediate error there. So I'm not sure why we have nothing on the screen. One thing it could be is if I forgot when I did my loading to write the texture handle back into the asset. That might be a little too easy, so I'm going to go ahead and guess it's not that, but I'm going to check anyway. So in here, we get the texture up, and then we produce the texture handle. You can see us do refer to texture here. So then we've got the asset, and, well, you know what? I'm right. I mean, there's the asset. I don't know why we're re-finding the asset here when we already have the asset. So that's kind of neither here nor there, but... so that's probably what happened, right? This texture here wants to be set. You know what I mean? So that is what we needed, and we weren't doing that. So we kind of want to make sure that all looks good. I'm guessing we'll probably have more bugs than just that one. I would be surprised, but we'll see. So, it looks to me like we're at least loading basic stuff okay there, right? Like all of these fonts loaded through that path and they look okay. So it looks like the white texture, amusingly enough, didn't come through. So, hilariously, the easiest thing for us to download, we screwed up. Oops. So, I guess I'll take that, though, because that's a lot better than the alternative. So, let's debug the white texture. Why didn't that go down properly? So, here's us beginning the texture op. On the texture op queue, we set a 1-1. Oh, we just didn't set the texture handle. So on this op, again, we want to set that texture handle, refer to texture, and we want to do that. So, again, same bug in both places. What is the actual call there? Just texture? Yeah. So that gives us our white back, and so that's good. So now you can see, yeah, that working just fine. And so now if I go back to the build and turn on optimized, we're back in good shape, I think. Yeah. So that all works just fine, it looks like, and yeah, off we go. So now, the last thing that we wanted to do as part of this suite of things, we're not allocating texture handles still. We just use the pool, and when we're out, I think we just recycle ones, and it'll just be chaos. So we're going to have to make that work for real, right? We got to actually make that code not be completely broken. But to end this particular stream, because we've pretty much used up all the time, and I want to do a little bit of Q&A. I want to do the thing that I said I wanted to do at the very outset, which was allow us to re-import. And so when you change a file, just re-import, not have to restart the app. So I want to flush those texture handles out. You know what I mean? So if we want to do that, we now have the ability to do that pretty easily, actually. If I go back into the asset and make a really simple way of rotating through the assets. So you can see here, like when we rotate through, you can see here when we're coming through the list, when we do the free handle count, we would just assert when we run out. And so what I want to do is make it so that we will reload assets when we update a particular asset. We can say flush this texture handle and reload. Right. So what that requires of us is we need some way here of saying, look, unload a texture, flush a texture when we hit that case. And so in order to do that, I really just need, I think I just need a thing that's like unload, so we've got load bitmap. I really just need a thing that's like unload bitmap. And here it would just say, look, if I can get rid of this bitmap, and in that case, what I want to do is I want to take it from, I'm going to do basically the symmetric operation of this, where I take it from loaded to unloaded, rather than taking it from unloaded to loaded. So all I'm going to do there is say, look, try to change the state from loaded to unloaded, right? Actually, queued, I should say. So, it's got to be in a loaded state, and we got to change it to queued, okay? If it actually does, if it was queued, right, if it was ready to go, then, I'm sorry, if it was loaded to begin with, state loaded, there we go, then that means we did in fact change it to queued, which means now we can change it directly to asset state unloaded, but not before flushing its texture handle, right? And so here's where we would give the actual texture handle back. For now, we're not even going to do that, though. We're just going to do this, and we're not going to give it back. Right, so we're clear the texture handle, no texture handle yet. Now we're unloaded, you can't use it anymore, sorry about your luck. So when we do that unload bitmap, then you're done, and you can't use the bitmap anymore, and we have to load it again if you want to use it again. Now, what's going to happen when we come in here is, again, that clear and this state change, we kind of want those to be a little bit more fenced, probably. Again, not clear that we really care that they are, but just in case. There we go. We just fence the two of those so we can make sure that the clear completes before this does, so that the processor doesn't write them out of order, right? Not the processor, but the compiler doesn't switch the order. And so that's just keeping the compiler in line there so we don't get any unexpected reorganizations of the order in which those things do. And the right consistency on this platform should make that happen. Now, on another platform, you may have to make that be more stringent, but right ordering occurs properly on Intel, so I think you're pretty much just good to go. You just need the compiler to not step in and mess you up. So we can unload a bitmap now, which means that anytime we change a bitmap, we can call the flush on it. And so what we can do there is just say, hey, yeah, if we do an import, so on an HHA, we go in there and say, all right, we're gonna update one of these images. Then when it gets that asset out, you can see it get it here. I want to flush the bitmap if there was a bitmap loaded, right? So like first things first, just unload it, like it's gone, like get rid of it, okay? So there's the assets, there's the asset index, and so I just want to make sure no one tries to use the old image for this one that we've updated. You know what I mean? Pretty straightforward. So I need to change that to a bitmap ID. Don't really care about that because a bitmap ID just is the asset index. We should probably eventually just get rid of the notion of a bitmap ID altogether because it's just not actually really all that relevant anymore. But a little bit of type safety there maybe helps sometimes. Who knows? So now what we should see is that we run this stuff. The HHA, that's got the line through it there. I want to be able to update it. Let's see, unload bitmap. Let's see if we can make that stuff work as the last thing we do on the stream. So let's say I do import and save. Okay, that worked, but it didn't hit my breakpoint. Did I spell it wrong? I guess it was just because the compiler inlined it and O2 sucked it up. All right, well, hey, that's what I wanted, right? That's what I wanted. So now hot loading of textures just works, and everyone's happy. So we still need to allocate, we need to keep a free list for the texture handles. So, you know, yeah, you get the idea. So I think we're right where we want to be. Tomorrow, which I probably will do a stream tomorrow, we can go in and fix, we can now go in and add the save load for those align points. So, but that was pretty good. That was a good blitz. We got all the stuff done. I'm pretty happy with it. So I'm going to go ahead and go to the Q&A, and then I'm going to go home and go to bed. What is going on in your optimized build? What do you mean, what is going on? The same thing that's going on in the debug build? I guess? Can you be more specific? I can't say I know what you mean by that particular question, but I can try to answer it if you can elaborate. Are you optimizing assets? I just want to know what it looks like. So I guess what I would say is, oh, do you mean what is the difference between the optimized? So really the problem is that the Visual Studio compiler seems to have a lot of trouble with some fairly basic stuff. And I think, I mean, I guess I can't really say that's true. So it's not its fault. It's just we have some heavy duty lighting stuff in there that probably needs to be algorithmically optimized a bit. And that's really what is causing that difference. So if you take a look at the debug build, and you look at where the time is being spent, right? So here's the difference in frame time, right? You can see it's like dramatically different, right? But if you actually look at where that time is going, it's not like the whole build is slower. It's all just one function. It's just compute light propagation, right? So it's only the compute light propagation call that's actually causing the problem. And for whatever reason, I don't know that I've looked too carefully at what the actual difference is, but it's probably just a case of a lot of inlining. There's probably like a lot of function calls in that code that are happening because it's a math heavy code. And so it's calling actual functions for things like adding two vectors together instead of just inlining the math ops. And when you add all of that overhead, it's like, you know, way, way slower. Because instead of just issuing a couple multiplies and a couple adds, it's actually like setting up a stack, calling the function, returning from the function, setting up another stack, calling the function, returning from the function, right? So, you know, even though it seems like they shouldn't be that different, they really are because it's such a heavy workload loop. That's really all it is. If you want, by the way, for folks who want a moderated chat experience, TM, there is a moderated chat that you can go to, and it is here. So you can actually just IRC to the moderated chat, which is on Handmade Network. So MSVC just doesn't do all the inlining stuff by default. Sorry, I'm more of a web dev and don't get this level of stuff. Yeah, I mean, there are some things that are good about what it does and some things that are bad. And the way that I would explain it, so if it, again, if you're a web dev and you're not used to the low level stuff, let me just give you a small example of what I mean here. In terms of what's actually going on, right? So let's say I want to look at that compute light propagation call. All right. So here's the compute light propagation call, and we're talking about the actual parts of it that matter. It sets up. It's multi-threaded, so it sets up a work queue of stuff that needs to happen, and then the stuff that happens here is actually, it's actually these little threadlets are sitting there doing the work, okay? And so this is the actual majority of what is, this is all the time in our entire app. It goes right here, right? So, this is the problem. So if you take a look at what this code does in the two different modes, here's a loop, that's the outer loop, and an inner loop with the ray indexes and so on, right? If I set a breakpoint like right there, for example, just as a place to look, and I jump to that line of the code, here in the optimized builds, or actually, which one are we in? We're the debug build. Here in the debug build, if I actually look at what the processor will execute, so what I've done here, again, if you're unfamiliar with it, what I've done here is I've just said, look, show me what the CPU is actually going to receive as instructions, okay? Then what you can see is, as we sort of step through this code, you can see all of the things that are going to happen. So here is it loading some of this data out, right, of an array. And here is it starting to do some math. Now what you can see is, right off the bat, it sets up a stack frame and, okay, didn't want to click that. It sets up a stack frame, and right here, it's actually doing a call, right? So it's actually going to call out to this operator star, which is the thing that does this multiply, okay? And that jumps me all the way here. I've got to set up a stack frame for this function. So this is actually just preparing a stack frame. Here I'm doing this multiply in the longest possible way. I'm moving things in. Oh, it's even worse, right? We implemented this as a series of calls themselves, so they actually have to do calls because this is some SIMD stuff that we did. It's single instruction, multiple data. I won't go into what that is, but we actually have two levels. So we got to call again, right? And then finally, here is the actual call. That's the, not the call, the actual instruction. This is the only thing we actually wanted to execute. And look at how many instructions we had to plow through, right? It's nuts, okay? Now what happens if I look at the code that the CPU has to execute in the optimized build? So here's the code for the optimized build. This is it. 1, 2, 3, 4, 5, 6, 7, 8, 9. We're already at the mul. No calls, no nothing. There's the multiply, right? So all of that crazy stuff you were wading through, it's just this is all we were trying to do. And now it all happens. So you can see there's the mul, the mul, the mul, the mul, the mul. All those multiplies, every single one of those multiplies was that giant call stack had to happen again. It's just, so you're just flooding all of these instructions in there. And so, that's just the way compilers work. When they're not trying to generate optimized code, they just insert the boilerplate thing you would do. Oh, he overloaded operator star, so call operator star. Set up a stack frame, call operator star. What does that do? Oh, okay, that's another function. I'm not going to inline it, right? I'm not going to try and eliminate redundant reads or anything like that, right? So that's just how it works. And I wish there were some ways to get around that. Like, I wish you could say, look, this is just some syntactic sugar, just replace it always. I don't ever want you to actually call this thing. Like, just, insert the mul directly. We don't really have tools for doing that. So either you turn on inlining or you don't. Newbie question, wouldn't inlining every function call speed things up? Does the compiler do that when you turn optimizations on? No. So actually, inlining a function is not always a win. Inlining a function is only a win in certain circumstances. So what you have to remember is that code doesn't magically appear out of thin air. It has to come from somewhere, right? So inside the processor, there's a number of things that have to happen in order to execute an instruction. And the number one thing that has to happen, as silly as it is to say, is it has to know what the instruction is, right? I mean, it's got to know what the instruction you're trying to execute is before it can execute it. So, logical question, where did it come from? Well, the answer is that inside the processor, it has a set of registers, and one of those registers says where to get the next instruction from. It's called RIP, right? And that address is the location that it needs to read the next instruction from, right? Now, you may already know this, but it's important to mention it again because it sets up the reason why you don't always want to inline things. Okay, so if the processor has to fetch the instruction from there, well, what do we know about processors fetching things? They have to actually get them out of the memory of the computer, right? And we know that the memory of the computer is not as simple as just saying, oh, I go and get it and it's fine, right? There's a whole host of things that have to happen there, and some of them can be very slow. Main memory on a processor is very slow. If I had to go all the way out to main memory and all the way back every time just to find out what the next instruction would be, processors would run about 300 times slower or worse, right? So we can't do that. So what we do is the same thing, the processor does the same thing it would do with data. It has caches, right? It has caches. So instead of just main memory, it has these caches, and one of the caches is called the I cache. And that cache is responsible for storing instructions. It's an L1 cache. So there's a data side and an instruction side of your L1 cache. You know what this is, right? Hopefully I'm not using terms that are super out to lunch here. But just like I said, web dev, I don't know what the stuff is that you would necessarily know. But when you go to buy a processor, right? When you go to buy one of these, they've got specs, and we looked at this the other, maybe even this morning. I don't even remember when we looked at it, but it was recently. They got caches, right? And these caches are faster memory that's closer to the processor and easier for it to access, right? So here they are. You've got an L3 cache. That's the biggest cache. It's closest to main memory, furthest from the CPU. It's the slowest one of the caches, but still faster than memory. Got the L2 cache, smaller, only 1 megabyte, right? Total, and these are divided per core, so it's actually 256K, one for each of the 4 cores. But you don't have to think about that right now. Then we got the L1 cache, and that's split into 2 halves. One's for instructions, one's for data, okay? Now look at how tiny this instruction cache is. each of my cores, each of my 4 cores on this chip, an i7-7700K, a good chip, it's an expensive chip, so they're not skimping on the cache here. It only has 32K of instruction cache. Only 32K. So what does that mean? Well, when we need to fetch an instruction, we don't want to go to main memory. So what the processor first does is it looks at what's in the iCache. If the next instruction is in the iCache, it runs it. If it's not in the iCache, oh boy, we're in trouble. Now we have to sit around and the processor just has to stall until it can actually get an answer from either the L2 cache, the L3 cache, or God forbid, main memory, right? So, if you want your code to run quickly, it is absolutely critical that the hot loops of your code remain inside the iCache. You, under no circumstances, want to have to be spending time waiting for instructions to come in. That's exactly what will happen if you inlined everything in your code. Because now every single thing you do just gets bigger and bigger and bigger and bigger and bigger size-wise. So the iCache, this tiny little iCache, and then the L2 cache as well, and the L3 cache, all of those start to just get blown all the time. They can't keep your code in it. Your code is so huge and you're running through so much of it that you're constantly waiting on iCache fills, right? And it gets worse. Not only does waiting to fill the iCache hurt you, the L2 and L3 are shared caches. So the data, the actual data that you're waiting on, that data you're loading, not the instructions, but the data you're trying to operate on, it's getting evicted from the L2 and L3 caches to make room for your code, right? So the more code you have, the worse off you are for performance. You want your code to be absolutely as tiny as possible. So the actual answer is, if possible, you want to minimize how many functions you inline. And so the only time you really want to actually inline calls is when it's so time critical and you can save so many instructions that that bloat is worth it, right? And in this case, what you can see is you can also save code size sometimes by inlining if a lot of what the inline function was doing was boilerplate. So if it was really a meaningless function and it's just like one line of code, inlining it actually saves code space potentially because the amount of work necessary to set up the call and finish the call is more than if you'd just done the instructions. That's a no-brainer. And so when the compiler sees that, it will inline it pretty much automatically. But when the functions are larger, inlining is not so good. It's worth spending that boilerplate, those few calls on the top and the bottom to jump into a large function because you don't want to be duplicating that everywhere it's called. Does that make sense? Hopefully that makes some sense. And by the way, it's worth noting that the compiler is generally the thing that makes the inlining assumption. So I'll just close on a couple brief points and then we'll wrap up the stream. If you put inline in front of a function, it doesn't matter. The compiler doesn't care if you told it to inline it. The compiler will decide to inline it or not itself. So whether you put inline in front of something or not is not going to change whether it's inlined on most modern compilers. Maybe in the old days it would have, it doesn't now. So there are some things you can do to force the compiler to inline. Sometimes there's like a force inline keyword that the compiler defines, specific to the compiler. And if you do that, it will inline it. And the other thing you can do is just you manually inline it. You manually cut and paste the code in, right? And so what I would say is, generally speaking, let the compiler make the decision. it will make a reasonable decision in the average case. So just let it do it. Don't try to manhandle it. Just mark all your code as static or nothing. Don't bother putting inline on it. It doesn't matter. It's not going to matter. Let the compiler do its thing. When you're actually working on the most important loops of your code, when it comes time to really hand optimize those, just move the code that you want in yourself. Don't rely on the inlining, and you're going to want to organize that stuff yourself. Only for your very most important loops. That's generally what happens. And you're going to want to be doing that in the context of profiling, so you make sure you're not making a mistake by moving something in that should have stayed outside. Again, because knowing if you're blowing the iCache or things like that, you can't tell that without getting profiler data back. Either looking at performance counters or seeing if something gets slower or faster and so on. And so you at least need to put timing blocks around your code and look at those results to know whether you're making a difference there. Don't just guess. If it's a critical loop, don't just go, I don't know, inline's probably better and I inlined it. Like figure it out, right? By making good timing test bed and check. So, all right, I'm going to close it down. Thank you everyone for joining me for the episode of Handmade Hero. It's been a pleasure coding with you as always. I love those asset system changes. Oh, it's so much simpler now. It's great. We'll reuse the texture handles. Maybe I'll do that tomorrow because that's not that hard. So we'll go ahead and throw that in there. And then we're pretty good to go. We can play with the sound loading. Maybe we'll put sounds back in tomorrow. And we'll actually start playing sounds. That sounds like a good idea too. We got so much cool stuff to do. We'll put the saving in. We got tons of stuff. Tomorrow's going to be fun. I'm looking forward to it. Don't know when we'll do it. Whenever I get a chance. My schedule's been kind of crazy lately, so we'll see. But thank you everyone for joining me. If you want to follow along the series at home, of course, as always, if you want to, you can pre-order the game on handmadehero.org, and it comes with all the source code right now, so you can go ahead and play around with it if you want to try experimenting with the sort of stuff we're talking about in the series. That's about it. Hope to see you back here for the next surprise stream. I will post the schedule sometime soon. Until then, have fun programming, and I'll see everyone on the internet. Take it easy, everybody.